Today we're going to talk about conservation of energy. And this is conservation of energy in a closed system. So we said mechanical energy, we're talking about the total kinetic and potential energy. And what we're going to see is that energy can be transformed from one type to another. Now, when I say in a closed system, when we're doing conservation of energy right now, we're going to start off and we're not going to talk about things like in the air, like air resistance. We're not going to take into account friction and stuff like that for now. When you take college level physics, you will do problems like friction on an incline, and when you do, and you will have to take into consideration like the friction and everything else like we've done before, all into one problem. So the law of conservation of energy basically says that the total amount of energy of an object stays the same. Okay? Well, what's the total energy before? So the total energy before is the sum of the kinetic and the potential. And the total energy after is also a sum of the potential and the kinetic. Okay? So what we're going to say that, again, in an ideal system, and that's where we don't have friction and air resistance and everything else, that the energy can either be created or destroyed. Now, there's a lot of other forms of energy. And what happens is that there's forms of energy that we're basically not talking about in this class. Okay? Because when there's friction, what happens when things rub together like your hands? What do you feel? Heat. Is heat a form of energy? Yes. So again, we're going to see that in real life, energy is transformed into other types, but we're not going to be calculating those. Right now, we're just going to talk about mechanical energy. We're just going to be talking about potential and kinetic, so that's why we're calling it an ideal system, because those are the only two we're going to talk about. Okay? So a decrease in potential is accompanied by an increase in kinetic and vice versa. Okay, so here's an example. A rock weighs 110 newtons. So remember, this 100 newtons. This 100 newtons is actually the weight, which is mg. Okay? So I have a rock here, and it weighs 100 newtons. Now, on the top, I'm holding the rock up. So the rock is not moving. So if it's not moving, we know that kinetic energy is 1/2 mv squared. But if it's not moving and the velocity is 0, the kinetic energy is 0. The potential energy is mgh. It's the mass times gravity, which in this case they told us the weight. So the 100 newtons is mg times the height. Where do we measure potential energy? From the ground. Remember, the ground, we call this base level. So the potential energy, how would I calculate that? mgh. So mg would be 100 newtons times, let's just approximate gravity to be 10, because that'll make it, it's 20 meters above the ground. So 20 times 100 would be 2,000 joules, because a newton times a meter is a joule. So the potential energy at the top is 2,000 joules, but that's the total energy, because remember, the total energy is a sum of the kinetic and potential. All right, now the rock drops down to 10 meters. Now, let's say I want to calculate the kinetic energy. Well, I know that the potential energy is mgh, so it's 100 newtons times 10, which is 1,000 joules. But at the same time, I know that the total energy is 2,000. Remember, that's the total. So whatever I lose in potential, I gain in kinetic. So I already know that the kinetic energy is 2,000 minus 1,000, so the kinetic energy is going to be 1,000. Just before this hits the ground, I'm going to say that this distance to the ground is so small that I can't really calculate it, but it hasn't hit the ground yet. So if I want to do the potential energy is mgh, So mass times gravity is 100 newtons times the height, which I'm going to say 0. So the potential energy at the bottom is 0. But what I know is whatever I lose in potential, I gain in kinetic. So at the bottom, remember the total energy still has to be 2,000. So the kinetic energy is 2,000 joules. Now, what if this example said, what if I wanted to find the speed just before it hits the ground? Remember at the top, remember when we dropped objects and we used equations before to calculate the speed, how it hit the ground? Well, now we can calculate the same thing, but now we can use conservation of energy to calculate the same thing. So how would I do that? Well, what I would do is I would write my equation for kinetic energy. Kinetic energy is 1/2 mv squared. And I know I can rearrange the equation to solve for the unknown in terms of the known. So if I want to find v just before it hit the ground, I'll multiply both sides by 2, divide by m, and take the square root of both sides. So this is equal to 2 times 2,000 joules divided by my mass. Now, I don't have my mass, so what I'm going to have to do is I can calculate the mass by using the equation F of g is mg. So m is equal to F of g over g. So 100 newtons. And if you want, you can just approximate this. I'm just going to approximate this as 10. So 100 divided by 10 is 10. So if I put 10 under here, then I would be able to calculate this. So 2 times 2,000 would be 4,000. Divided by 10 would be 400. And then the square root of about 400. Now, if I wanted to count the velocity midpoint, I could do the same thing using the equation kinetic energy is 1/2 mv squared, right? And then rearrange it and solve for the velocity there because I know the kinetic energy is 1,000. Now, remember before when we dropped an object, when I initially drop it, the velocity is 0, but the velocity is going to increase because gravity is pulling it down, and it's going to increase, and just before it hits the ground, it's going to have its maximum velocity, Vf. So this is conservation of energy. So in layman's terms, the total amount of energy remains the same. Whatever I lose in potential, I gain in kinetic, and vice versa. Now, there's all kinds of energy transformations taking place all around us every day. So here are some examples of some energy transformations, and then the type of object or how this is being done in our everyday life. So we see that from chemical to electric is an example of a dry cell battery. Electric to chemical, see this is the converse of that, is a battery recharger. Mechanical to electrical is a generator in a power plant. Because a generator in a power plant, you have turbines that are moving and they're turning mechanical energy into electrical. And then the opposite of that, electrical to mechanical, is an automobile motor. Mechanical to heat, moving parts in a machine, and then heat to mechanical is a steam engine. Heat to light, an electric light bulb, and then light to heat, a laser drill. So again, these are just a few examples of energy transformations that go on every day in our lives that we don't realize. And we're going to see that there's just not one energy transformation. There's many, many, many different types of energy transformations. This is another example that's in your notes, and it's pretty much the same thing. So if I'm going to work a problem like this for homework, when I read the problem, I'm going to take every little part and I'm going to write it down just like I do every other problem. So I'm going to write my given. I'm going to write what I want to find. I'm going to write my basic equation. I'll rearrange to solve for the unknown in terms of the known and substitute and solve. So it says a large chunk of ice with a mass of 15 kilograms falls from a roof 8 meters above the ground. A, what is the kinetic energy of the ice as it reaches the ground? And B, what is its speed? So I'm given the mass. Gravity is 9.8 meters per second squared, and the height is 8 meters. Now, first I could write, if you want to first, so you remember the equation, because you don't want to say, ooh, this is such a long equation, you can write, in layman's terms, the total energy before is equal to the total energy after. And then write the total energy is a sum of the potential and kinetic initial, and that's equal to the potential and kinetic after. So the potential energy before is mgh. The kinetic energy before is 1/2 mv squared. Now, what I like to do is, before I start filling in a bunch of stuff, I like to say what's zero. So at the top, the chunk of ice isn't moving, so this goes to 0. And then at the bottom, just before it hits the ground, the potential energy is 0. So now I've made my equation so much easier. And then I can rearrange the equation. So when it says, what is the kinetic energy of the ice as it reaches the ground, you can see by the equation that the potential energy at the top is equal to the kinetic energy at the bottom. Okay? And then you can substitute and solve. And then when I say, what's the speed, you do just like we did a second ago and rearrange the equation and solve for the speed. And that's it. So this is conservation of energy.